The contents of lecture 6 consists of the following. We will begin by classifying partial differential equations in terms of quasi-linear or nonlinear partial differential equations. We will see that most of our problems are quasi-linear in nature, and we will talk about the classification of PDEs by taking various examples. We will start with a system of equations involving first derivatives. So, we will have more than one dependent variables, and of course, there are more than one independent variables for all PDEs that you know. We will see that quasi-linear PDEs would be classified in three types: either they are parabolic or elliptic or hyperbolic partial differential equations. Having defined what these are and what are their properties in terms of the characteristics, we will talk about systems with second derivatives, and as an example we will explain this with the help of boundary layer equations. Having classified the PDEs, we will talk about the basic requirements of solution methods. One of the prime requirement is noted here, that this problem has to be well posed. Despite this classification and well posedness of the problems, we will also notice that classification is not everything, because of certain features by which numerical solutions are obtained. So, we will quote few examples. For example, heat equation will be solved by one of the easiest method, which is called the FTCS scheme, or forward in time, or centered in space schemes. We will identify what is known as the computational molecule of this particular algorithms. We will also take another example from elliptic PDEs, and that is the Laplace's equation. We will once again show how its characteristics is obtained and what is its molecule, and how the unknowns are ordered in solving the problem. And again further classified, if they are linear, that is very easy to see that dependent variables in all the terms appear as linear functionals, whereas nonlinearity is also equally understood. In contrast, you have the third class, which we call as the quasi-linear PDEs. Quasi-linear PDEs are essentially nonlinear PDEs, but in the highest derivative term they appear as linear. Okay? And this may appear as a kind of a severe restriction, but you would find most of PDEs that we come across in various branches of science and engineering happens to be quasi-linear PDEs, and quasi-linear PDEs have been easily classified. A systematic theory exists, whereas nonlinear PDEs are not so easy, but some specific classes of nonlinear PDEs have also been analyzed. So, let us look at classification of quasi-linear partial differential equations. As I told you, these are the PDEs where highest derivative terms are linear. So, for example, talk about a test case, an example where u and v are the dependent variables, and independent variables are x and y as given by these two equations. And please note that according to our definition of quasi-linearity, all these coefficients that we have here, a1, b1, c1, d1, f1, and a2, b2, c2, d2 and f2, they would be of course in general function of x, y, but because of quasi-linearity they could be also function of v and u. Okay? So, in a sense it is nonlinear, but in the highest derivative terms that you see here, u x, u y, v x, v y, they appear linearly. So, that is the appellation that we call it quasi-linear PDEs. Now, a very simple urge for us to know that if we have this governing equation and we prescribe some starting conditions and we prescribe some boundaries over which the solution is defined, and the solution is progressed, and let us say we have reached the solution up to this curve gamma. Okay. So, that could be some parametric curve which I call t equal to gamma. Now, the solution is known in this well. The question that we ask is can you advance the solution beyond gamma? That is one of the aim for this. If we want to really find out, so what we have seen that u and v are functions of x and y, and what we could do is knowing the solution up to gamma, we could go beyond it by just simply writing out a Taylor series, okay, where the first derivatives could be obtained from, let us say, the governing equation that you are given. The higher derivatives, what you could do is you could keep on differentiating these equations and generate auxiliary equations for higher derivatives, right. So, if I want to get u x x, I would perhaps differentiate this once, and then I go about trying to obtain those. Okay. So, now going back to this figure again, let us say focus our attention on this point P, where we know the solution, and along P Q also we know the solution, right. So, if I migrate from P to Q, taking this increment d x and d y, then along that line P Q, what we could do is we know what is d u and d v, right, because we know the solution at those 2 points. Those we could relate to increments due to d x and d y via these partial derivatives there. So, now what we have, we are trying to figure out all these 4 derivatives which we stack them up here, okay, and these first 2 rows are nothing but the governing differential equations that we have, and these 2 are those auxiliary equations that we just now concocted. So, these are the 2 last equations. So, what happens is trying to figure out those partial derivatives, you just simply have to solve this linear algebraic equation. So, that is a fairly easy thing to do. What we need to do is however to observe that equation that we have written down, which had this particular form. We have u x, u y, v x and v y, and on this side we had f 1, f 2, du, dv. So, this could be solved for this, provided we can get A inverse, right. That is what solving that linear algebraic equation means. However, the solution process will break down if this matrix A is singular. So, we demand that this matrix be non-singular, then only we can get those solutions for those partial derivatives. So, stated another way, that we talk about the scenario where the matrix is singular at some point or some part of the domain, then what happens? We cannot uniquely determine this quantity, and that would amount to acknowledging that we have some kind of discontinuities. The discontinuities will occur whenever your matrix is singular. If that is happening at a point in the domain, from that point onwards we could work out lines along which this discontinuity can propagate. When such lines exist, we call those lines as characteristic lines. We ought to remember though that we are talking about discontinuity in terms of the derivatives, but the function by themselves, the dependent variables are continuous. So, please do not misconstrue about this point that we are making about discontinuity. This discontinuity is about the derivatives, not about the function itself. we did talk about little bit about shock waves, hydraulic jumps. There are many such examples where you actually see discontinuities in the physical variable itself, but these characteristic lines are not those discontinuities. These are discontinuities of the derivatives. So, essentially then the existence and the properties of these characteristic lines can be evaluated by looking at the determinant of that matrix, and this is what we get. And as you can very clearly see that we could write this equation 4 as a quadratic in dy dx. Okay. So, if you write it as a quadratic in dy dx, then what happens is, starting from the point P, you can work out this quantity dy dx. It is quadratic, means you will have 2 of them. So, you can figure out from the point P if the derivatives are uniquely determined or not. If those slopes are real and exist, they do exist, then of course, you say that these lines specify the directions of propagation of derivative discontinuities. This may sound a long drawn phrase, but it actually means the following. What is your differential equation telling you? When we write out a governing equation, what do we actually mean by the differential equation? Differential equation basically tells you how the information or the signal is propagating. So, if I have line of discontinuity in the domain along those characteristic lines. So, what is happening along those lines, my information is propagating. So, that I have one set of value to the left, another set of value to the right, and characteristic lines are those lines along which these discontinuities are propagating. Okay. So, we can now look at various sub cases. If this determinant is positive, then you have a couple of real and distinct slopes, and emanating from that point you have 2 directions along which these discontinuities propagate. And when you have such a scenario, you call those PDEs as hyperbolic partial differential equations. This is something which you probably have done it, but let us look at it from computing point of view once again. If of course, the characteristic determinant is equal to 0, that is the quantity under the radical sign, then of course, these 2 slopes are going to be coincident, and such a PD will be called a parabolic PD. This is also quite known to us. The third possibility of course, is D is negative, and then the characteristics that you are going to get are going to be complex, they are not real. So, you do not have discontinuities propagating along real lines. What does that mean? This means that you do not have, suppose I have a domain like this. So, if I am looking at a hyperbolic or a parabolic problem, I would have information propagating along characteristic directions, and when I do not have them, what happens then? The solution here or anywhere would not be realistically dependent on its neighbors. Instead, what it would do, it would depend upon all the points in the domain. So, it is not only this point is determining this point is determining this, but this point is determined by all the points in the neighborhood, and subsequently each one of those points are determined by their own neighbors, okay, the continuum of the points, and in the process you would find that eventually the solution anywhere depends on what you prescribe on the boundary, right. So, you can see elliptic PDEs are those what we already have called them as a boundary value problem, where the solution depends on the boundary conditions. Okay. So, that is why these are also called the jury problem. I may like to tell you a little bit of a story here. When originally these elliptic problems used to be solved, and in the absence of computers, they used to do it with the help of human assistants. These assistants used to position themselves in a room in a sort of a lattice network. So, what will happen is each one of them sitting at one point would get the information from the neighbor, like what I just now said, that it would be dependent from information coming from all directions. So, one person sitting there in a network gets information from the neighbors, then use them on a particular algorithm. We will find out how these algorithms are developed in the near future, and then that person will evaluate what the value would be for the next step. And when everybody is done, everybody is agreed upon that we have arrived at the next time step, then the conductor, the professor who is to do that, Professor Souther, one such person in Cambridge, he used to do that, and I will tell you an interesting story. He used to penalize those people who used to make mistake in their calculations. So, at the end of the day, there are lots of those assistants would collect negative salary over the day for making mistakes. So, anyway, that is what this jury problem comes about. So, everybody sitting in their room is a jury. When they decide together that we have achieved our task for one time step or one iteration, then the jury agrees and the problem is settled. So, that is why historically elliptic PD is also called jury problem. That is a legacy of history. In contrast, actually if you have hyperbolic PDEs, there is a possibility that you can reduce those PDEs into a set of ordinary differential equations along those characteristics, and these equations are called compatibility equations. And there is a vast literature and a subject called method of characteristics, which actually depend on this methodology, and we would not be talking about it because they also have their limitations, because the following, that in real life any problem that you encounter, you would hardly ever see that you have only one type of PDEs governing the equation. What I mean is your governing equation may be same, but in different part of the domain you are going to see that some part it might actually behave like a parabolic PDE, another part it is going to be elliptic, some part it could be hyperbolic, and so on and so forth. And if such a thing happens, then you realize the mixed character of the problem would not allow you to come out with a generic solution procedure for such a mixed problem. In fact, one of the most spectacular development has come about in the field of fluid mechanics, and believe me, till 1971 people did not know how to solve a mixed flow problem. So, that was a starting point where people could handle flow in a domain where part of the domain you have a hyperbolic equation, part of the domain you have elliptic equation. So, basically that is what I was saying, that method of characteristics being very well developed, but it only works in the hyperbolic part of the solution. So, it requires your knowledge where it actually starts. So, that is part of the solution. In many cases it is not so easy to work out, although in some cases people do have some advantages, and they do start from a specific region of the domain where you would know for sure that from this line onwards you would have hyperbolic nature of the PDEs. Well, let us work out some examples. This is probably you have been taught time and again in your course on PDE, that this is a second order PDE on a single variable u. So, you have the pure derivatives and the mixed derivatives appearing together, and what you would be doing once again, first and foremost, I think may like to take a little relook at the problem. When I mean that, recall that diagram we drew, that in this let us say we have a solution like this. When I say I have solution up to this point, what exactly do I know? Say for this equation, if I say I know the solution, what exactly I know at P? Do I just simply know u? I also know the derivatives. Which derivatives? We know those derivatives which are 1 degree lower than that appearing in the differential equation. So, that means when I say I know the solution, so I know not only u, I also know u x as well as u y. Okay. So, please do remember how do you define what we mean by a solution. So, in the previous case, if you recall that we obtained two auxiliary relations here. So, what would we do here? In this case, for this particular problem, then we would be writing it down in the following manner. Let us first identify what are unknowns. So, we are trying to evaluate these as unknowns. So, one of them is given here is A, B and C. On the right hand side we have F. Okay. Now, what we are saying about the solution means we also know this dux. So, what is dux? Dux would be uxx dx plus uxy dy. So, the second equation of course will have a coefficient here dx, and here we will get dy and here we will get 0, and the same way the third equation we will write it down is duy, and that will have 0 here and dx here and the dy here. Okay. Now, you can investigate the determinant of this matrix, and that gives you this equation. So, once again you come out with that quadratic for dy dx, and the characteristics are then given by this, okay, b plus minus square root of b square minus 4ac by 2a. I have noticed among the students have this tendency to show them a partial differential equation. The first thing they try to do is find out b square minus 4ac, and if it is not in that form, they are full of panic. So, you please do understand that this is a very specific example where this particular form comes in, and again you can classify based on whether this b square minus 4ac is positive, 0 or negative. You notice one thing though, that if we have b equal to 0, then the equation that we get is the well known Poisson equation. Poisson equation is a very prototypical elliptic equation, appears in many branches of science and engineering, and we ought to know how to solve it. Now, this is something we have done already, and I made that remark that the work done by Prandtl was revolutionary. Why we will shortly see. Remember that the boundary layer that we had obtained had two equations, one originating from mass conservation that gave us ux and vy here, and the x momentum equation we wrote in terms of this. And what we now see when we are trying to solve this equation, in this equation 6, of course, you have the highest derivative is this. So, again it is a quasi-linear equation, right. Left hand side are those nonlinear terms, but they are of the lower order. The highest order is the second derivative. So, that is why we call it as a quasi-linear PDE, and we rewrite it for convenience in this form nu y u y y 0 into u x y and 0 into x x, and these are the things that we will assume known, because that is what is our definition of solution is. Now, in addition we could also write this couple of auxiliary equations dux and duy. So, we get again a 3 by 3 matrix equation, and what do you get? You get this, and as you can very clearly see that you can expand it about the first row, and then you get this nu into dx square, and very clearly you can see now the characteristic directions are coincident because both the roots are the same. So, dy dx will be infinite or dx equal to 0, that means x equal to constant is the characteristic direction. So, that is what I told you that if I had this problem of a flow in a domain, I could just simply march, go from one x station to the next, because the information is propagating along constant x line. So, the moment I realize that, I would actually solve this first equation along x equal to constant, and once I have that solution at a particular x, from there I go to the next station. Okay. Why do I have to go to the next station? Because in the next station I would require this derivative, that is why I need the solution at the previous step. But remember, the information is propagating along x equal to constant, but not across. So, that is why wherever I would have this kind of derivative u x, I will be actually discretizing, thinking of the following, that look at it this way. Suppose I have the problem like this and this is my x direction. So, I would get the solution at x equal to constant. So, this is my y axis. So, if this is the region, I would solve it here at all those points, and then we will migrate to the next line, and wherever these quantities are involved. So, if I call this line as 1 and this is 2, and if I have to obtain u x, I will just simply write it as u 2 minus u 1 by delta x, because that is what this is telling us. You see, that is using the knowledge of the nature of the solution, that we should not try to get information from here, that would be violative, right, because this is a parabolic equation. We can only get information from what happened before, not what is going to happen in upfront, okay, downstream. So, this is something that you realize that what happened. Now, supposedly what we have obtained in boundary layer approximation was, if you recall, that we actually dropped one single term here only, right, that was nu times u x x. That was our boundary layer assumption. Boundary layer theory gave us that we can safely drop u x x in comparison to u y y. Suppose I would have retained that u x x here, then what would you have obtained? You would have obtained here a nu in the 1 1 location, right. So, if I look at that, so what I have for boundary layer approximation, this is nu, and if I wouldn't have if I wouldn't have obtained made that boundary layer assumption, then I would have also had a nu here. Now, you try to work out the characteristic determinant, what you would find. Okay. So, this will give you okay. So, what you are seeing then, what comes out from this, if we would not have used the boundary layer approximation, then our characteristics would have been complex. It is basically a boundary value problem. So, we would have had to solve the whole domain together, but the moment we make that boundary layer assumption, we are going to march. So, this is what happens, that from a boundary value problem you end up getting a marching problem. So, this is the marching that you are going to undertake along x equal to constant lines. Yes. So, will there be a line of discontinuity? That is what we are saying, that discontinuity is propagating along this line x equal to constant. That is what characteristic lines imply. What exactly we mean by two solutions? They are same, they are coincident, isn't it? Yeah, they are coincident. That is why you have a single line, right. So, you see some of these classifications help quite a bit. Now, having said all that, why we are not that enthusiastic about this classification, I will just spend a little time and explain to you. Let us say we want to solve this heat equation. The heat equation is simply given as u t equal to u x x, right? And so, if I see the solution, then we are talking about the solution being dependent on x and t, and if I say I have the solution up to some point in x t plane, that would involve the knowledge of u and u x, right. So, we know this. So, this is your solution. So, if I were to write a similar equation, first we should write down the unknowns. Unknowns are u t and u x x, right. And if I look at the governing equation, of course, it is here 1 and there is minus 1, okay, and this is 0. What would be our auxiliary equation then? We will come from here, we will write du. Du would be u t dt plus u x dx, right. So, how would I write it? I will write it as u t dt should be equal to du minus u x dx, because this is known. So, right hand side is essentially known to you. So, what you would do, you would write this equation as here dt, and here of course is 0, there is no and on this side, right hand side, we will have du minus u x dx, right. And it is very easy for you to tell me that the characteristic direction is given by dt equal to 0, and that corresponds to t equal to constant. Okay. So, basically then the solution that we look at would be plotted in the x t plane. So, I will plot x in this direction and t in this direction, and as you know, in most of the heat transfer problems, that you would be probably the simplest possible problem is this one dimensional thing. I mean, you have a rod, you hit from one end and then you try to get the solution. So, the length of the rod will tell you the region where you are interested. So, you would be given the solution here at t equal to 0, that is your initial condition, and then of course, you would be prescribed your boundary conditions here and here. Okay. So, the characteristics suggest that your information propagates like this. Okay. Now, if we are going to compute this equation, how do we do it? Let me tell you, solving heat equation, one of the earliest successful attempt was by what is called as forward in time centered in space. So, this is what is called also in short form FTCS algorithm. So, we talk about now how we implement it. Okay. So, if I talk about the solution at cell time level t of n, and I would have discretized this problem along some network of points, and then I say that I have the solution along this line, and we are trying to find out what is the solution here, right. So, what I would do, I would represent the solution u of x and t at let us say x equal to x j and t equal to t n. Okay. So, what exactly means that we are identifying x also with the index j, and let us talk about these are uniformly spaced lattice. So, we have this as some kind of a delta x, right. So, this will denote it like u j n. Okay. This is definition. This is pure definition that we lump the system in discrete points, discrete times, and we associate indices, subscripts like j of n. So, that indicates that solution at the location x j at time t n. Okay. So, if I am trying to evaluate this quantity del u del t, this I would like to do it, let us say at that point x j point and at this time. So, basically if this is let us say my jth index, okay, if this is my jth index. So, we are talking about writing the derivative about this point. Okay. One of the easiest thing that we have learned just recently was to use Euler integration. Remember, that is what we said, that was the easiest way of discretization, and that is what we are also saying here, forward in time. So, what we would be doing, we will be still restricting ourselves at the jth point, but we will write this derivative like this. Okay. So, that would be that. Now, we did also say about using Taylor series as a means of discretization for derivatives, spatial derivatives. And if you remember, we wrote it down like this, u of x plus h as u of x and delta x u x and so on and so forth. We could keep on adding many more terms. Now, what we could do is we could also similarly write the unknown at the left point. Then what you would find that the odd derivative terms appear with a altered sign, and so on and so forth. Okay. Now, one of the easiest ways is just simply add it up, then you are going to get u x plus h plus u x minus h. On the right hand side, you will get 2 u x, and notice that all these odd derivative terms will cancel, this will cancel with this, and the first term that you are going to get is delta x square by 2. So, a couple of them will give you this. The next set of term you will get 2 times, and the fourth derivative term, right, and so on and so forth. So, what happens is I can see that from this equation we can write u x x would be equal to u x plus h. I will pull this over on the other side and divide by delta x square. Then whatever the term that we have left over, that will begin with delta x square, right. So, what we have just figured out that we can keep this u t here and then make use of the Taylor series expansion that we have obtained just now. So, we will write that as u x x at x j and t n. We are only varying x, keeping t the same. So, I would write that down. So, what this would be? This will be u of j plus 1, right. This will be u j, this will be u of j minus 1. So, u of j plus 1, n is the same, right. So, twice here. Okay. So, we got this. Now, you see what we have obtained. We have now replaced the continuous differential equation in terms of a lump parameter system, where the values are lumped at those nodes intersection of this lattice, and that is what we are going to write u j n plus 1 minus u j n. I will write this quantity here, delta t by delta x square, and in parenthesis we will have u j plus 1 n to u j n and u j minus 1 n. So, that is easily done now. So, what we are seeing now, u j n plus 1 is nothing but u j n plus this quantity that we have written down, right. So, basically we are saying that the unknown quantity at this location, that is what your left hand side is, depends on the function values at the previous time step at this point that we have already identified, and also it depends on the two neighboring points of the previous time step, right. So, in computing, this is what is called as a finite difference method. In the finite difference method, you work out what we call as the computational molecule. So, this is your computational molecule. What does the computational molecule suggest to you? How is the information propagating? We have just done this classification and we have figured out the information should have propagated along t equal to constant line. Are we getting that here? If I were trying to figure out the solution at this point, then my information should have come along t equal to constant line. But instead what we are getting information from this. It is coming from a region which is given by the apex at that point and these 3 points. Now, you see what happened in the previous time step. this point was evaluated by getting the information from these 3 points. This point was evaluated from these 3 points, and this point was of course evaluated from this. So, what you notice that information seems to be confined in a wedge, and what is that? That is your typical hyperbolic PDE kind of behavior, right. So, what is happening from each point, we are finding out 2 characteristic direction along which the information originates. So, for example, this point will influence those points which will be in this wedge. So, although we are solving a elliptic PDE, in our actual solution procedure we are mimicking a hyperbolic PDE, and there is a price to be paid for this. Why we are willing to pay the price? You can see there are certain features coming out of this difference equation. This computational molecule written like this is also called the difference equation. So, from differential equation you come to a difference equation, and what you also notice that the difference equation are some kind of a linear algebraic equation. That is what we have obtained. However, what you notice that this particular way of evaluating the solution at advanced time level from the information from the previous time level is an explicit procedure. I had the information at nth level, from there I could just directly take one point at a time and evaluate it explicitly by using this difference equation. This is an explicit method, and that is what you are paying the price, that you have tried to get a solution of a parabolic PDE by an explicit method. In the process you ended up mimicking a hyperbolic PDE, and that puts in some kind of a restriction on the time step that you can take. What you usually like to do is you would like to take this time step as small as possible. Then what will happen? This characteristic line, these lines will open up, right. They will, as you reduce delta t, your this hyperbolic characteristics will approach their parabolic limit. You see that? So, that is the reason why you have to keep your delta t as small as possible, right. So, that is the story. That is the story, that you try to simplify, you have to pay somewhere else. And one of the things that I just now demonstrated to you is a case where, although you want to solve a parabolic PDE, your method was not really taking the benefit of the classification. Well, you are taking the benefit by saying I will have delta t as small as possible. That is a knowledge, okay, but we can see also the restriction arising out of that activity. Okay. What we could have done, of course, we will do it in a lecture, maybe in 4 or 5 lectures downstream. We will come back to these and show you how we can discretize. You can see that what I have demonstrated here is one possibility, one particular algorithm I have shown you. That is not the end of the world. There are many possibilities by which we can solve the differential equation. So, one of the easiest and the simplest one I showed you, and I showed you its limitation, and I showed you that we many a times in computing we try not to really follow what is embedded in the governing equation, and we try to do something artificial, and we have to be cautious about doing that. This is one example that I told you. Now, having obtained this expression for u x x, let me draw your attention to another problem. This problem is another very simple equation which is prototypical of elliptic PDE, and that is this. What is known as, let us say, the Laplace's equation. I could also keep the right hand side and have a Poisson equation. So, if I try to do that, now what I could do, I could write this solution again x j and call it as y n, and I will write it as u of j n like this. Then what you are now noticing, that your computational domain is in the x y plane. And just for the sake of simplicity, let us say we have identified a region like this, and the first step will be, of course, deciding where, how many points we would like to deploy in getting this computed solution. So, we discretize the domain like this. Okay, let us look at, say, this is my jth point and this is, let us say, my nth index in the y direction. So, we are focusing our attention on a point like this. That is what we are doing here, right. Now, this equation, what we would be doing, we would be writing again a similar kind of a module, right. Of course, here y is involved. So, when I am evaluating u x x, I keep y constant. So, I have omitted here, but you could write out a y in all the index. At the same time, when you are trying to figure out u y y, you will keep x constant and you will write a Taylor series in the y direction. So, in the x direction, when I try to do that, I see that these 3 points are involved in u x x. And when I am trying to discretize this, I am going to involve these 3 points. Okay. So, what you are seeing here, that you get a computational molecule here now, like this, and this is what is called as a 5-point molecule. That is a very elementary discretization one can think of. It is used even now time and again. So, that is your 5-point molecule, and what you notice that if I write that equation down, then I will write it as u j plus 1 n minus 2 u j n plus u j minus 1 n by delta x square. And we will write u j n plus 1 to u j n plus u j n minus 1 by delta y square. Okay. So, that is equal to 0, and when you write it down, you find out that your u j n, if I write it down, put it on one side and 1 over delta x square plus 1 over delta y square, keep that 2 outside, and on the rest of the quantities we could just simply write look, the way this equation is written here, if I were to stack the unknowns, now this is an elliptic problem. So, it is a boundary value problem. So, I can't do any of my other tricks that we have used in the heat equation or used in the boundary layer equation. What will happen? Each point will be influenced by the 4 neighbors for this kind of discretization. If I write down all the unknowns, so what I will require boundary conditions here. I will come back to this boundary condition, very interesting topic at a later time, but let us say we have information available on U on all the 4 sectors of the boundary, and then what will happen, my unknowns will begin from here, right. This is the way the unknowns will be described. So, what this would be? This would be j equal to 2 and this will be n equal to 2. So, I would have my unknowns which will go like u 2 2 and so on and so forth. So, I will have u 2 3 j I am writing first. So, next point would be 3 2. So, we are following a particular pattern. We will write it like this, first row wise, then we will increment the column. This is what is called as a lexicographic style, but we just ran out of time. So, we will spend a little time talking about this issue and we will end this and we will move over to discussing something new.